Okay, so let's get started. We're going to be taking a look at working with understanding our volumetric efficiency table within our airflow model, understanding what the values in here actually represent, and learning how we can have a sanity check on our work after we've done our calibration and tuning process. Now, I'm not going to dig into how to actually calibrate and tune the volumetric efficiency table in this tutorial. We're going to be digging in that to the next tutorials coming up here in the training course. For right now, we want to understand conceptually what is going on and how these values translate into this engine load calculation. So first and foremost, we have our underlying fuel and airflow model equation. Fuel mass is equal to air mass divided by target air fuel. The airflow or air mass is going to be estimated knowing a couple different variables. So we have to know the map pressure, we have to know charge temperature, which is going to be a combination of the ambient temperature plus a couple other correction factors. We have to know number of cylinders, engine displacement, and then finally, we also need to know our percentage of cylinder filling coming from our volumetric efficiency value here in our table. What we're going to find is if we combine all of that, we can calculate an estimated air mass. So we'll find that that's going to be represented here as engine load. So that would be our air mass. So if we know air mass, and we would know the fuel stowage and the desired target lambda, multiply stowage by target lambda, gets us actual target air fuel. So air mass divided by target air fuel gives us a fuel mass. We can convert the fuel mass into an injector pulse width, knowing the injector flow and the fuel pressure or estimated fuel pressure, which will affect the injector flow, and any of the latency or short pulse width data. We put all that together, we get a corrected pulse width. We pulse that to the injector, it sprays fuel into the engine, and if everything is in line and balanced, meaning we have all of our variables accounted for and calibrated correctly for our speed density, airflow modeling, and we have correct volumetric efficiency values in our table here, and our injector data is valid for the injectors we're working with, we will hit the desired target lambda spot on, and we won't have any fueling differences. But if we have anything out of line within our air temp sensor, or map pressure sensor, or even engine coolant temp sensor, if anything's improperly calibrated there in terms of the sensor calibration, or if we've expressed the engine displacement incorrectly, or if we have our volumetric efficiency values here not dialed in correctly, we'll ultimately find that we're not going to hit that exact fueling that we're requesting here from our fuel mixture aim. So just to keep things as simple as possible here, when we are tuning our volumetric efficiency table, our job is to move the values up or down to be able to hit the desired target lambda here. But there is more going on than that. So we can actually have, let's say, a bad injector data, or have, again, something ain't properly calibrated, map pressure sensor, intake air temp sensor, engine coolant temp sensor, and we can find that we can bake in these types of essentially errors into our volumetric efficiency table. So the only way we really have to dial in and tune within the Motec and getting our fueling right is to move these values up or down in our table. We want to make sure that the values that we're entering in here do make sense, because this is an estimation of airflow. That's what the values in here essentially are going to express. If we're moving our values up, we're essentially telling the Motec that the engine is ingesting more air. If we're moving the values down, we're telling the Motec that we're not having as much air entering the engine, and that will linearly affect our fueling. But the values that we do place in here, again, should make sense, and that's essentially what I want to get through with this training module. I want to make sure that you understand and be able to do a sanity check on your values coming from your table. Now, the best way to take a look at this is going to be at least looking at the idle portion of our table. We can go in at idle and get a fairly good idea if our volumetric efficiency values here in the table make sense or not. Now, we can take a look here. The volumetric efficiency values I have in my table, I'm showing my inlet manifold pressure right now with my engine idling here about 900 RPM. It's about 54 kPa. So we see my cell point is operating right here in the table. So it's going here and it's averaging between these volumetric efficiency values. I would expect my VE values to be anywhere from about 45 to 65% at idle conditions. Every engine will be a little bit different in terms of the proper volumetric efficiency value, but that will get you fairly close. What we can find is the expressed engine load that's calculated is 210 milligrams. That's how much air mass we're estimating coming into the engine. We can take this value and actually run it through a calculator that I've put together to see if the values that we have here within our VE table, as well as making sure our other parameters are going to have valid readings. If everything's good, we should find that we have a valid grams per second reading. So grams per second is going to be something we typically find for looking at a mass airflow sensor. That mass airflow sensor will be directly measuring the airflow coming into the engine.
Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here. And you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.